Hello everybody, today we are going to study the functioning and working mechanism of central processing unit called CPU in short. Before we talk about CPU, let us revise the components of a digital computer. A digital computer consists of input devices like keyboard, mouse and output devices like monitor, printer and main cabinet unit consisting of CPU, memory and I/O controllers. The main cabinet unit contains connectors and ports for connecting various input-output devices. Whether the computer is a small palm top, laptop, desktop, the central component of the cabinet unit is a single chip microprocessor called CPU. Powerful computers like mainframe or supercomputers often contain multiple CPUs. These machines are used to perform parallel operations so as to serve concurrent multiple users or perform a complex computation in less time. All the mobiles, whether a low cost mobile or costly smartphone, contains a microprocessor which is a single chip CPU containing computing as well as signal processing capability. The user enters the input using input devices in a desktop computer. The information is stored in main memory. The CPU processes the information in memory by executing the program placed in the memory. A program is a sequence of instructions written to accomplish a particular task. The processor executes the sequence of instructions one by one to complete the execution of the program and produces the desired results as output of the program. The results produced by the CPU are stored in the memory. These results are then shown to the user with the help of output devices like monitor. The computer functioning is completely controlled by the program under execution, except the interruption by the operator or input-output devices. The objective of today's topic is to understand how CPU works, how an instruction is executed by the CPU. Before we understand how CPU works, it is essential to understand the architecture of the CPU and its main components. The architecture and the components vary from one CPU to another and from one manufacturer to another. However, there are common components in every CPU which are necessary to perform computation and are necessary to understand the working of the CPU are explained next. There are 8 common components in every CPU, which are number 1, arithmetic and logical unit, floating point unit, control unit, prefetch unit, decode unit, internal cache, registers and bus interface unit. These components and their logical interconnections help us to better understand the working of CPU. However, looking at the physical structure of the CPU, it looks like a single chip with large number of pins connecting system buses and the mechanism for dissipating heat with fins and coolants. The above components are integrated with the help of millions of transistors inside the chip. The first component, as I explained earlier, is arithmetic and logical unit called ALU in short, is used for arithmetic and logical operations. The arithmetic operations like addition, subtraction, multiplication and division are performed by ALU. The operands required for these operations are given to ALU either from internal registers or memory locations. The results are also stored in internal registers. The Boolean operations like AND or NOT comes under logical operations. For example, if AND operation is applied between two numbers expressed as binary 1110 and 001, the result of the bit by bit AND operation is 0000. Similarly, if the OR operation is applied between the two binary numbers 1110 and 0001, the result of the bit by bit OR operation is 1111. These operations are also used to compare numbers and find out if the given numbers are equal, greater or less. The arithmetic operations involving decimal numbers are performed by floating point unit FPU in short. Most CPUs today have multiple ALUs and FPUs that work together concurrently to perform various arithmetic operations. The second important component is control unit, which coordinates and controls the various operations and activities taking place within CPU. For example, in order for the ALU to perform arithmetic operations, the first step is to transfer the operands from registers to ALU. The second step is to perform computation. The third step is to store the result back into the register. The control unit ensures that the second step starts only after the completion of first step and so on. In short, the control unit ensures the strict sequence and timing of various operations taking place in ALU, FPU and various other units of CPU. The data transfer between CPU and memory are also controlled by control unit through timing signals. The control unit derives the timing signals from an external unit called system clock. The system clock is a quartz crystal located on the motherboard. The system clock generates a square wave which changes from 0 volts marked as 0 to 5 volts marked as 1 every specified time period. If the time period is 1 millisecond, it generates 0 volts for 500 microseconds and then 5 volts for next 500 microseconds to complete the cycle of 1000 microseconds, which is equal to 1 millisecond. A system clock having a time period of 1000 microseconds will change its status from 0 to 1 and then back to 0 1000 times in 1 second. Therefore, the frequency of system clock is referred to as 1000 Hertz. These days, the system clock rate used to drive the CPU is measured in gigahertz. 1 giga is 10 to the power 9. Even the CPU used in the small mobile phones runs on gigahertz clock. The time related operations governed by control unit are synchronized with system clock. A CPU with higher clock frequency processes more instructions in 1 second than the same CPU having lower clock frequency. However, the higher frequency system clock can be attached to the CPU only if the CPU is designed using a technology which is capable of faster execution of the instructions and is able to synchronize with the faster clock. The third important component is prefetch unit. The prefetch unit fetches the data and instructions in advance so as to avoid delays in processing. The fetching in advance eliminates the speed mismatch between CPU and memory. The next component is decode unit. The decode unit receives instructions from the prefetch unit and identifies the type of the instruction to be executed and accordingly instructs the control unit and ALU. Another component of CPU is internal cache. The cache memory is a fast memory residing between CPU and main memory. A part of the program to be executed is placed in cache memory. The multiple references to the same part of the program by CPU are served by cache memory instead, which is faster as compared to random access memory. Through the cache, the speed mismatch between CPU and main memory is eliminated and program runs faster. Earlier, the cache memory was external to the CPU, but these days the cache is internal to CPU and designed as two-level hierarchy. These two levels of cache are termed as level 1 and level 2 cache. The level 1 is faster memory and is closer to CPU as compared to level 2 cache. Another important CPU component is the set of registers. The registers inside the CPU are used for storing temporary information. They are also used as operands for arithmetic and logical operations. The register contents may be transferred as input to ALU or FPU. Also, the results generated by ALU or FPU may be stored in one of these registers. Later, if needed, these register values are transferred to main memory or output devices. These registers are also called fast memory locations inside the CPU. Next important component of CPU is bus interface unit. The bus interface unit is a place where the instructions and data flow in and out of CPU. It connects CPU to the system bus so that it can communicate with external cache, RAM and the rest of the computer. The CPU executes an instruction with the help of 4 internal registers. First is program counter, second is instruction register, third is memory address register, fourth is memory data register. The program counter register keeps track of the execution of the program and holds the address of next instruction to be fetched from memory. We can also say that logically program counter points to the next instruction to be executed. The instruction register holds the instruction currently under execution. Its output is given to the control circuit, which generates the timing signals that control the various processing units involved in the execution of the program. Next, the 2 registers MAR and MDR, memory address register and memory data register, facilitate the communication with the main memory and connects to the bus interface unit. The MAR holds the address of the memory location from where the read or write operation is to be performed. The MDR contains the data to be returned to the main memory or to be read from the main memory. Next, as explained earlier, a program resides in main memory and usually is brought there from hard disk or into other input device. The execution of the program starts when the program counter is set to the first instruction of the program. The contents of the program counter are transferred to MAR, which is memory address register, and read control signal is set active. After the access time is elapsed, which is the time required for the memory chip to perform read operation and deliver data on the data bus. From the data bus, the contents are transferred to MDR. Then the contents of the MDR are transferred to IR, which is instruction register. The instruction once brought in IR is ready to be executed by the CPU. If the instruction requires the operations to be performed by ALU, it is necessary to obtain the operands. ALU cannot add 2 numbers unless until the 2 numbers are given as input to ALU. If an operand resides in the memory, it has to be fetched by sending its address to MAR and initiating read operations. The desired operand is brought from memory and stored in MDR. It then is transferred to ALU. The ALU performs the operation and generates the result. The result may either be stored in one of the registers or memory location. The storing of the result in register is directly performed during the execution of the instruction. However, if the result is stored in the memory, the address of that memory location must be returned to MAR, write signal is activated, the data is returned to MDR. After the access time T, which the memory takes to write, the result is stored in the specified memory location. As soon as the current instruction execution is over, the value of program counter is incremented in a manner that it points to the next instruction under execution. The CPU, using the program counter, starts working on the execution of the next instruction. In addition to transferring data between main memory and processor, the computer accepts data from input devices and sends data to the output devices. Thus, some instructions involve handling input and output operations from the devices directly. The CPU is capable of executing a large number of instructions. These instructions are referred to as instruction set. Some instructions govern the transfer of information between memory as well as memory to IO devices. The other instructions specify the arithmetic and logical operations. Normally, by default, the instructions are executed in a sequence one after the another, but there are instructions to change the flow of control. The instruction involving change of flow of control change the value of program counter so that the program execution begins from a new location as pointed to by the program counter. An instruction for its execution requires data. The data could be integer or decimal number expressed as binary. The alphanumeric characters are also stored as binary numbers only. several coding schemes are developed. Two of the most widely used coding schemes are ASCII, which is American Standard Code for Information Interchange, in which each character is represented as 7-bit binary code. The IBM mainframe uses a different coding scheme, which is called EBCDIC, the Extended Binary Coded Decimal Interchange Code. In EBCDIC coding scheme, 8-bit code is used to represent a character. In short, whether it is a data or the instruction, at CPU level, they are sequence of binary digits only. The CPU interprets the binary sequence as instruction if it is pointed by the program counter. If that instruction brings another binary sequence as operand, it is interpreted as data by the CPU. This is the reason it is said that CPU understands the binary language only, language of 1 and 0. In some situation, a program may also be interpreted as data if it is processed by another program. The example of the above task is compiler. A compiler transfers a higher level language program into machine level program. The machine level program, which is sequence of instructions in short, is then executed by CPU. During the compilation, the entire high level program is treated as input data by the compiler. Each instruction typically consists of 4 general operations. These 4 operations are fetch, decode, execute and store. These 4 operations are often referred to as machine cycle. The CPU is capable of executing one machine cycle in one system clock cycle. That means a modern CPU is capable of executing up to 1 giga or 10 to the power 9 machine cycles in 1 second. As explained earlier, the first step or the operation is to fetch the instruction from the cache RAM. Next step is to decode the instruction to identify which one out of the hundreds of the instructions in the instruction set is fetched and is to be executed, and accordingly informs the control unit and the ALU what to do. The next third step is the execute unit, which performs the execution of the instructions. The fourth step is store, which stores the data or the result from the ALU to either register or the memory location. In old CPUs, these steps were completely sequential and the instruction was executed only after the execution of the previous instruction. But the modern CPUs can process the multiple instructions in overlap time span using the concept of pipelining. In pipelining, the next instruction fetch starts immediately after the previous instructions fetch. Fetch is complete and it goes to the decode unit. Using pipelining, the 4-stage instruction execution as explained above is broken into 10 to 20 stages, and ideally the instruction execution rate in a k-stage pipeline can be improved by a factor of k if the successive instructions are overlapped. The another concept which is used in modern CPUs to increase the execution speed is to use more than processing components, more than one processing components like ALU, FPU, control unit and decoding unit on a single chip. The CPU with 2 processing components is called a dual core CPU. The CPU with 4 processing components is called a quad core CPU. The presence of multiple processing units facilitates simultaneous arithmetic and logical operations, leading to increased capability of handling multiple programs or users. Also, the techniques can be used to divide a single large program among multiple cores and finish the program in less time. So, to summarize, what we have studied today are the components of digital computer. One of the important components of any computing platform, whether it is laptop, palm top, tablet, desktop, mainframe or supercomputer, contain central processing unit, which is CPU in short, as explained earlier. The CPU is also called a single chip microprocessor, because most of the computers these days have single chip microprocessor used as central processing unit. Also, we have studied the various components of the CPU and how these components connected together executes an instruction. The step by step execution of an instruction leads to the execution of the program to produce the desired results, which are made available to the user through output devices. Also, we have studied how CPU distinguishes between instructions and data, and how instructions and data which reside in the memory are brought in the CPU for execution. The concepts like pipelining, multiprocessing to increase CPU performance were discussed in short. Thank you.